Now we'll talk about some notion of normalization and regularization that we want to use in with linear discriminants and in general in machine learning. So, with this kind of model where we have these weights and W and W0, under some circumstances, the values of the weights can explode. They can get really, really big, or can implode, can be really, really small. So, for example, we know also that we are in a case where we are over parameterized, in the sense that we are working in a space of d dimensions, but we have d+1 parameters. So there are multiple configurations of weights, W and W0, that give us the same classification. So we will classify the same way. The sign of h of x will always be the same for the samples, but the weights are internally different, and the magnitude of h vary. So we can get, I would say, values with a big h or small h, but if you just care about the sign of what h is giving us, it is equivalent in terms of classification. So this kind of, I would say, explosion or implosion of the values of W0 comes from like making repeated corrections to the weights. We kind of apply multiple corrections that will get us with maybe values that are getting bigger and bigger. So with some criterion, in fact, also we can get, I would say, lower errors with lower weights. So as the value of h is getting small, the output it gives, or x, is getting smaller and smaller, close to 0. The sign is right, but the error is lower. So we've got some error criterion that may behave that way, which is not a good thing. And having this, we may get in situations where the values will exceed what can be represented in a computer. We will get what we call overflows or underflows. It means that the values are beyond what can be represented. We have 10 power of something really big, or 10 power of something minus something really big also, which are really, really small values, which are not properly representable on a computer. And that is a problem, because we will get numerical errors. It will get unstable, or will just not work properly because the values are overflow or underflow. So possible solutions to deal with that will be to normalize, for example, the weights at each iteration. So we can say, okay, we are making an update, but we are kind of readjusting the weights after each update to get, I would say, an unitary vector. So this is what we are doing here. We get the W value normalized as W prime, and this is in fact divided by the norm of the vector W, including W0. So this is nice because it will kind of get the weights to always being unitary after each update. And at the same time, if we just look at the sign, it will not change the sign. Usually the behavior will be the same. We will classify the same way all samples, but the magnitude of h may vary according to that. We can also standardize the error criterion. We can just get the error as the error divided by the magnitude of x, because sometimes, like overflows may come from the fact that our x's are really big. If we are dealing with big x's, and the x is including in the update, it may mean that we are adding always big values to the weights, and this is where they may start to explode and going into overflows. So with such criterion, we will kind of standardize the error, and we'll get the error lower. So we will reduce the impact of the x's over the error that we are computing. So this is a way kind of to standardize, not without standardizing directly the data. We are kind of normalizing the effect of the data on the error, and that may help to avoid being in troubles into like with numerically unstable algorithms. There are also other approaches which are dealing with limiting the weights values during optimization. For example, what we call a ridge regression. In ridge regression, we try, for example, to minimize the least square criterion here. So we are minimizing the least square criterion here, but we have something special here. We have a constraint. We see that our optimization is constrained by the fact that we want the sum of the squared weights. so the sum of the value of the weights squared, to be less than some kind of gamma value. So we want to be less than that gamma. This can be made into an equivalent formulation, you know, assuming that the gamma is not directly defined. We kind of put it in some ways with a lambda that is replacing the gamma to get, I would say, a sum of the usual error, the usual least square error, plus the summation of the weight square. So this will kind of build up a new error where we will, minimize the least square, but having some kind of regularization on the weights values. So this is interesting because it will force the models to go toward what we would consider as simpler models, because if some weights are not that useful, they can be disabled, or at least being not really used in the decision by getting their weight to be really low. So we can somehow disable some features, some variables from the model by using this kind of regularization. Because in some cases, we can get some correlation, you know, where a positive value for one variable is canceled by a negative value from the other. And basically in the decision, they are not counting, but in the model, we take them into account with possibly a positive value for WI and negative value for WJ, even though they are completely correlated. So with ridge regression, we should be able to kind of avoid this. We will disable these two variables because they are both canceling themselves in the model, while they are not useful apparently because they are correlated completely. So this can be applied assuming that the data is standardized first. So we should center the data on the origin and be sure that they are corresponding to some kind of normal distribution with standard deviation of 1 on each dimension. And we don't necessarily have to use the least square here. You know, this is the standard example, but, you know, we can make use of the kind of regularization, that thing here, with different error criterion, just kind of using our error plus some factor lambda, the sum of the weights squared. We also have what we call LASSO. LASSO is the same idea, but using what we call a L1 regularization. So instead of getting the weights at power 2, we've got the sum of the absolute value of the weights. So we're just kind of summing the values of the weights, not taking into account their sign, and using this as a regularization over, for example, the least square criterion that we saw before. So the thing is, a sum of absolute values cannot be used directly in the partial derivatives. You know, we cannot get derivative directly from that, contrary to the regression where something at power 2 is easy to derive. So we need to use some other optimization approaches like quadratic programming that can deal with that well. The nice thing with LASSO, it is even stronger than ridge for eliminating variables. You know, the variables will really be set to 0 with such function because their absolute values will count a lot, and then getting them at 0 will disable the variables and will reduce, somehow will get this error to be lower if the variables has no impact on the classification or little impact. So if we compare here, we have what we call the L2, which is basically the ridge regression. So we can see that square here is basically a square where kind of values are equivalent. And the thing to look at here is that according to our criterion, the point that will minimize the error will be on the dash red line. And so we see here that the values for weight W1 is close to 0, but non-zero. We have some kind of small values here that is non-zero, still quite low, compared to L1, which is the LASSO, where we see that in fact it is completely disabled because the point which is minimizing the error is really where W1 will be equal to 0, while W2 has some values. So that's the difference between, that's a way to explain why LASSO is really disabling variables, while RIG is reducing their value, reducing their impact, but not necessarily completely disabling them. You know, the weight is relatively, can be still there with a low value. So that's, I would say LASSO is better for disabling variables, but harder to manage in terms of optimization because we cannot get the partial derivative with that formulation directly.